And hello everyone, welcome to this video of convection boundary layers. So this is a very important topic to learn in convection heat transfer. So in normal convection heat transfer, again, it's very similar to our fluid mechanics. You will have some correlation. Okay, so for example, if you have some heated tubes, alright, some heated tubes. It's very common to have heated tubes in a heat transfer geometry. So, and then you have some fluid flowing at U infinity here. Okay, so what is the heat transfer? So usually you will have a heat transfer coefficient H, which is watts per meter square per Kelvin. Okay, or these are SI units. You can change it to whatever units you like. Okay, so it's energy per unit area per unit what do you call that? Conduction. No, not temperature. I must be getting sleepy. Alright, so this is what is usually calculated, and it's usually given by some Nusselt number, Nu. Nu equals to some function of Reynolds number and the Prandtl number. Okay, if you're not sure what these are, yeah, you have to go. You have to check that out in other videos. I'm not going through that in this video. Okay, or this video series for that matter. You should already know what these are. And Nu equals to some H times some length dimension over K. So this is the Nusselt number. Okay, I assume you know this, basic one. So you have some fluid flowing at U infinity, T infinity, and this rods will be maybe at some surface temperature, Ts. And on the object, what you have is that some people do experiments and then they'll find Nusselt number correlations for H. And how do you then find the heat flux? The heat flux will be equals to H, okay, Ts minus T infinity. Okay, so this is just the temperature difference. Okay, I think there should be some minus signs in here. I'm not really focusing on that right now. But the idea is that heat flux, you have to kind of indicate directionality and all that, and it flows from high temperature to low temperature. Okay, so heat flux is actually proportional to the temperature difference, okay, with this constant of proportionality. It's not really a constant, but it's a proportionality factor called the heat transfer coefficient. Okay, so just notice that the minus sign actually comes from the fact that heat is always, almost always, net heat is always going from high temperature to low temperature. So in this direction, temperature increases, but the heat flux actually flows this way. So why is there a minus sign? It's because the direction of increasing heat flux and increasing temperature, they're opposite. Okay, so that's just a note why there's a minus sign. Okay, so if this is from this heat flux, I have not defined what it is. If it's this formula, it will be from fluid to surface. Okay, why? Because the temperature difference is defined as surface temperature minus the fluid temperature. So they have to be kind of going opposite. Okay, this is the rough idea. Okay, not so sure whether, yeah, you have to check do check if this is correct. But when I say fluid and surface temperature, that kind of idea. So yeah, just let me know if I made a careless mistake here again, but the idea is the same. Alright, so for normal heat transfer situations, you have a lot of these correlations, right? This sort of gives you averaged heat transfer coefficient. And even for a fluid flowing through a tube, for the most of the time you have some Nusselt number correlation that can give you that rough number, right, of the heat transfer coefficient. Unfortunately, I mean, this does give us a very good rough idea, a good estimate of what the heat transfer coefficient is. But if you really want to understand convection in depth, all right, you want to understand convection in depth, then you have to look at boundary layer. Okay, boundary layer. Okay, in most of the flows here, in the middle of the pipe, you will have something called fully developed flow. Fully developed flow. But near the entrance region, it is not really fully developed yet, so you'll have to think about boundary layer as well. So this is important, right? This is important because you kind of want to know, okay, roughly how effective heat transfer is maybe across a fin. So you have some fluid with some temperature, U infinity and T infinity, it will flow across a fin. It will create a boundary layer. So this is a fin at some maybe a constant temperature or some other thing. Okay, so you kind of want to analyze what's the heat transfer coefficient across this fin, and having this boundary layer theory will help you to have a good baseline, baseline of comparison. So we are doing laminar boundary layers. Okay, no turbulence or anything like that. So these are like the basics of boundary layer. Okay, and same as per the fluid flow, standard fluid mechanics, we usually like to deal with flat plate flow problems. These are the most basic ever. Okay, so I have those actually covered in my, how do you say, in my GitHub repository. Look for the heat transfer theory YouTube. It should be inside the description. Okay, under heat transfer theory YouTube, I have at this point in time some videos about radiation and some videos about fluid mechanics. Okay, but without further ado, let's start. Okay, so we start first. You kind of need to know Navier-Stokes equation. Okay, Navier-Stokes equation and how to reduce them to this. I actually have in my fluid mechanics videos, I discuss how all of this is done using the order of magnitude estimates. Yeah, so to solve this set of equations, you use the Blasius similarity solution. I also discussed what these equations are. So all of these equations, along with their boundary conditions, they are reduced to these solutions, and the velocity profile is given by these what do you call that? Yeah, this expression here. Eta is the similarity variable, while f is the dimensionless string function. And I did derive this previously, but the shear stress is given by this expression over here. I just kind of copied it over from this textbook. Okay. Of course, that's not the only way. You have von Karman as well. So this is the von Karman equation. Again, derivations I did in another video. And from these, you can actually look at your boundary layer thickness. Okay, from the approximate solution, which is the von Karman solution, and the Blasius solution, you actually have two different sets of results, but they are very, very close. Okay, so that's what you need to know first. Okay, before we start. Okay, so when it comes to convection heat transfer, the first thing you'll probably have to consider is energy. I mean, heat energy, right? You want to consider heat energy transfer. Okay, and the unit of choice, or the variable of choice that we like to use, is called enthalpy. Okay, enthalpy is equals to the internal energy plus PV, is the pressure times volume. Of course, these are specific enthalpy and specific internal energy and the specific PV work. Okay, and so this is all of these are in a per unit mass. Okay, specific volume is volume per unit mass. E is internal energy per unit mass. H is enthalpy per unit mass. So hope you should know that. Yeah, and of course in thermodynamics we often like to use the term U for internal energy. Yeah, when we do our thermodynamic correlations, our Maxwell equations for thermodynamics, we like to use du equals TdS plus PdV, something like that. So U is often the symbol used for internal energy, but we want to avoid using that because it looks way too similar to this U over here, even if we do a capitalized U. Alright, so we don't want to use U, we want to use E instead. Okay, we want to use E, which is the internal energy. Okay, so normally we with the heat transfer equation for convection, we start with an enthalpy balance. Yeah, we start with enthalpy balance. Why do we use enthalpy? Because we don't have to consider flow work, this PV work. Okay, across this. Okay, so what is this flow work? I just very quickly try and give you some intuition. So flow work is like the energy you need to put this thing through in the system so that it occupies the space. Okay, just for example, you have a ball of air. You have a basketball, maybe a basketball. Alright, you have a basketball filled with air. Alright, so and what are you trying to do to try and help you visualize flow work? So if you have a basketball in air, and then it will be like this. I don't know how to draw properly. If you try and submerge it underwater, you feel that there is some force that you're trying to push against, and that force is known as upthrust. Which is buoyancy. Alright. What is upthrust? Okay, the total upthrust. Okay, in air, of course, there is some upthrust, but we neglect the upthrust in air. So, but in water, there's very significant upthrust. So, what's this upthrust over here? Upthrust equals the weight of the fluid displaced. Okay, so you're forcing this ball into the water, and you feel the upthrust, and this is rho Vg. Okay, rho Vg. Okay, so this is part one of the thing. Okay, and of course we neglect the weight of the ball as well. We neglect the weight of the ball. We only consider the weight of the water. Okay, we are thinking that the ball is very light and all of that. So, and of course the upthrust in air is negligible. So this is actually rho Vg, but I want to since we are talking about PV work, this is P is actually rho Gh, at least in this case, hydrostatic pressure, rho Gh, right? So what is rho Gh? You notice we have a rho G over here, rho G. All right, and then we have V, and you notice this upthrust is actually a force. Okay, so just to give you an idea of what it feels like to do some PV work, it's basically like forcing an object into another medium. That's what PV work is like. So this is force, and the distance that you force it into, well, that's you can roughly gauge by the height of the water, right? Okay, depending how deep you push it in, yeah, depending how deep you push it in, so that's how much work you kind of need to do. All right, so rho G Okay, force times distance, the distance is h. Okay, so okay, so the idea of PV work is like that. So you see rho g h v. Okay, so rho g h and v, you see both of these are very similar expressions. So it's not, again, it's not an exact, really a correct way of a physically so accurate way of thinking about it, but this should help you give some intuition into what this PV work is like, because it can seem very abstract. Okay, so okay, so that's about PV work. All right, so this thing is we call it flow work. Oh, better don't cancel flow work. And yeah, so how is this enthalpy balance being done? Okay, H equals E plus PV. All right, so so we have the substantial derivative term here. Okay, the time derivative, and of course the advection term over here. Okay, this is contributed to by the conduction of heat, the generation of heat, if there are any chemical reactions or whatever sort of reactions, or a heat generation mechanism. Okay, due to chemicals or some other kind of reactions as well. And we have dissipation, because you know, when there's friction, friction actually contributes to the heat. Okay, friction actually contributes to heat. So if your fluid is moving so quickly and there's so much friction, it will actually raise the temperature of the fluid, just like it will for maybe a lubricating system. Like when you press brakes on a car, or press brakes on maybe the aeroplane. Aeroplane has wheels, right? So they can press the brakes there as well. Because the wheels are spinning so fast, the fluid can actually get hot from these wheels. So that will actually contribute to increase in enthalpy of the system. But for our case, for the most simple cases, we can actually neglect these two terms. Okay, we can neglect these two terms. And okay, you can neglect these two terms. All right, so so let me put neglect heat generation and dissipation. Okay, this is a heat generation per unit volume and dissipation per unit volume. And the next thing is what we want to do is to consider this conduction term. And as you should know, conduction is done using Fourier's law. Okay, Fourier's law is like so: K delta T. And conduction is the conduction term. How much heat is being contributed to via conduction is this this term over here. The negative of the divergence of the conduction heat flux. So let me just make it clear. Conduction heat flux, okay, is over here. All right, so if you really want to be so general with these equations, you can even include radiation heat transfer or radiation heat flux as well, but we are neglecting. So also neglect radiation heat transfer, because radiation can also heat up the air or heat up fluid. All right, so we're not going to consider radiation heat transfer as well. That kind of complicates the problem a lot. Okay, so just a reminder, heat flux is Q. We use this Q double prime, and I'll put it like so. Heat conduction is like that. Okay, and maybe I'll just put the radiation on top, just to radiation. So we'll just substitute this expression in for Fourier's law. Okay, and of course I want to give it a subscript. Okay, so conduction. Okay, so now we just substitute Fourier's law in, and we'll get this equation. Okay, the minuses will cancel out. The minuses will cancel out, and we'll get these ones. Okay, so the first thing we want to say it's K, the heat conduction coefficient, is isotropic. Okay, because usually in general heat conduction here is a vector, it's not a scalar, so to speak. But in this consideration, we actually consider it to be a scalar. So it's a scalar because you have such thing as an anisotropic heat conduction, but in fluid you don't see that as much. Okay, so because it's very homogeneous, it's mixed and randomized. Okay, so almost at 20 minutes, but let me finish this. Okay, so and we also assume K does not change with X, Y, or Z. So K is same everywhere. Okay, K does not change with the X, Y, and Z. So we can bring this K out, and then we'll get nabla square. Okay, nabla square T, and that's the Laplacian of temperature. All right, so okay, so that's what we have, and of course H. Okay, we know this. Okay, delta H equals to rho Cp dt or delta T. Okay, delta H equals to rho Cp delta T. This is the specific one, and well, delta H can also be counted like this: H minus H ref, because in thermodynamics we always need to consider a reference point. Okay, for these intensive variables, we consider a reference temperature. Okay, and this is what the correct way is, I mean the more full way. Okay, so H is equals to the following. Okay, it's equals to the following, but we note reference temperature and enthalpy are constant with time, x, y, z, etc. Okay, all of these, the T ref and the H ref, they are constant. Okay, so if you substitute all this in, the reference temperature and reference enthalpy, everything will disappear. Okay, and you'll just get rho Cp T. So we didn't just substitute in this very carelessly. We actually gone through some thoughtful consideration. Okay, and then more or less we are done. We are almost done. Okay, and if we assume density and heat capacity. Okay, so this term, it's also, I think, this is heat capacity per unit mass, and this is rho. Okay, and the product, okay, the product of this is called volumetric heat capacity. Rho Cp, we call it volumetric heat capacity. And we assume the volumetric heat capacity doesn't change with time, x, y, z. Okay, because Cp is actually heat capacity per unit mass, but rho is actually mass over volume. So this whole thing is actually heat capacity over volume. Okay, this is joule per kg per k. This is kg per meter cube. Right, so if you want to see the units in SI units, here you go. Your wish is granted. Okay. So so you see that the kgs will cancel out. Then you have a volumetric heat capacity there. Assume volumetric heat capacity does not change with x, y, or z and time. Alright, doesn't change with x, y, and z, or even changes with time. It's not always true, yeah. This is a simplifying assumption, because sometimes when the temperature increases, your heat capacity and your density will for sure change. But we are simplifying it a lot for our analysis, so that it make life easier for ourselves. Alright, so if we assume this, we can actually factorize all of this out and divide through. Okay, so divide through, you have fraction k over rho Cp. Okay, and this is actually a very special important unit or term. This is called A. This is called alpha, or thermal diffusivity. Alright, alpha equals to k over rho Cp. Again, this shouldn't be too new to you. I'm just revising some of the basics. And there you go. Okay, so we'll just replace the Laplacian term here. Okay, we'll replace the Laplacian term. So partials, this is in Cartesian coordinates, and then we are done for this video. So let's do this, and Laplacian is finished. And that's how you get your temperature equation. Okay, so this is the conduction term, this is the advection term, and this is the time derivative term. Okay, so this actually covers our preliminaries before we can start our boundary layer equations. Okay, so thank you. I'll see you again. Bye bye.